Welcome everyone. In this video I will try something different with the stacked Peltier coolers. I was not really satisfied with the previous experiment where I could only reach -40 degrees on the cold side of the top Peltier device, and I strongly believe that that should be different. And the reason why I reached such a bad temperature on the cold side is because I could not really find the DT values for the hot side of the device, which is in the bottom. So I was feeding too much power to the system, and first of all I was not pumping the heat in the best ever way, and also I was providing too much current maybe, and therefore I was like overheating the whole device instead of really just focusing on the heat which is just sufficient to pump the heat from the top stage. So now I will do a different approach, and I will try to estimate the hot side temperatures by some measurements. So what I do now is I already have the power supply running for a while, and I'm waiting for some equilibrium temperature. So while I'm waiting, I can tell you what can you find on this test bench. So this can be familiar to you if you are following my videos. If you are not, please subscribe, and you can follow these kind of let's say cool projects. So what you can see on this test bench is we have a thermometer box which has 4 different thermometers. One is here, this is the number 4, which is measuring basically the ambient temperature, and then the number 1 is here in between 2 fins of the heatsink. So that is measuring the cold side temperature of the top stage of the Peltier cooler, and also it's combined with a K-type thermocouple which you can read on this screen. And the thermometer which I use here as a chip, it's an LM335 unit. I made an entire video of building this thing, so please check that out. You can find it somewhere in this corner. And then we have channel 2, which is here, 29 degrees. That's basically the exiting temperature of the air which is passing through the radiator here. And then we have the channel 3. I have the pump here, and also the tank, the reservoir for the water, and I put the thermometer inside the water, so it's really close to the pump or to the bottom of the tank. And then that is showing 29 degrees, as well as this thing, which is almost at the same temperature as the other thermometer, and that this blue screen is measuring the temperature here. So this is basically the exiting water from the aluminium block, which is cooling the hot side of the bottom stage of this kind of composition of Peltier units. So what is inside this box? We have an aluminium cooler in the bottom, and that is connected to this water cooling system. And that aluminium cooler is a water cooler is cooling the hot side of the bottom stage, which is a TEC 12715 Peltier cooler. So it's a 15 ampere unit. And on top of this, so on the cold side of this Peltier unit, there is I put the hot side of the TEC 12703, so 3 or 4 ampere unit, and then the cold side is in contact with the heatsink here. And the heatsink has 2 purposes. One is basically to clamp down these 3 different things, so the aluminium cooler block and the 2 Peltier devices, and also it's very easy to surround it with this foam, so it gives some structural rigidity, and I can also put the thermometers in between the fins. So it's very nice that I can really measure everything nicely, because the sensors are sitting tightly in between those fins. So I assume that they are measuring the proper temperatures. So that can be found there. And what I have on the power supply now, right now, the only thing which is running is the bottom Peltier unit. So the top Peltier unit, the 3 ampere unit, is just acting as a piece of material now, and it just conducts the heat, but it is not connected to the power supply. The power supply of that unit is not running, so there is no power flowing through that device. There is no cooling from that device. And you can see that based on the K-type thermocouple, we can read 0 degrees Celsius, and based on the LM335 chip, we can read minus 3.8 degrees. And this has been the temperature for a while now, so I can imagine that this is the equilibrium temperature for this specific settings. And what I will do now, I will measure the current which is flowing through the wires here, and I will measure the voltage with this, and then I will try to sort of reverse engineer what is the DT with this kind of voltage and with this kind of current. So let me measure these things, and I will tell you in the video what are the values. So I just set up the current meter. .74, so 474 amperes, which are running through this device. And let's see the voltage. .506. So let me write this down. So now what I will do, I will calculate, I will check the DT based on the graph performance chart. I will check the P equals U times I, but that is roughly 25 watts, let's say. And I will check what is the QC at this setup. And then I can tell you that now, as the water is really low, 28.8, I can tell that this is the hot side temperature as well. So the hot side temperature of the TEC 12715 is let's round this thing up, and let's say that it is 29 degrees. So we note down this value as well and do some evaluation. So now I do the evaluation, and then I come back. I will change the current, and we wait another few minutes to have the temperatures to become stable, and we do another set of measurements, and then we conclude something. So first of all, we can physically see that this temperature, which let's say is equal to the hot side temperature of the bottom unit, is 29 degrees, and these temperatures are between almost -4 and 0, so let's say -2 degrees. We can say that the DT based on this is 30 degrees. If I use the voltage values, voltage and the current values, I also get the same DT based on the chart. So that means that my method of reading and understanding the chart is probably good, so far at least. So this is correct now, and if we can believe the chart, then we are somewhere around 18 watts of cooling power. And remember, from the calculation, which is the first video of this part of the series, we got something like 83 watts required. So we have to go back, up more. But what I do, I just slightly increase the current, and let's say I want to reach 7 amperes or 8 amperes, and we wait again to get everything to reach the equilibrium, and I do another set of calculations, and we see where we end up. So now I increase the current, or I increase the voltage because the current is already maxed out. I mean, I have to change the voltage in order to increase the current. So then I change it, and I will stop somewhere, let's say around 8 amperes. So let me measure that. So I have this nice guy here, and I try to measure it. Okay. So this is our current, 8.04, and then let me read the voltage. 623. So I will note down these values, and I let this system to run for a while, and after that I will come back and discuss what will happen next. So I think I waited enough and the temperature is not really changing anymore. So I just recently measured everything. So the current is 7.87 amperes and the voltage is 6.22. So I leave the clips on the power source or on the cables which are running through the Peltier, so I will always measure this, at least for the bottom unit. And then the water temperature is now 31.2 degrees, but it's not changing anymore, or maybe it's just changing very, very slowly. So we can say that this is the sort of equilibrium or the hot side temperature. And then what I can say more is that the K-type thermocouple is measuring minus 6.6 degrees, and the chip is measuring minus 10 degrees. That can come from this difference can come from the different kind of clamping between the different kind of temperature sensors and the heat sink. So maybe the contact for the K-type thermocouple is not so perfect. And then the water temperature is 30.8 for, that's 30.8 for the outlet temperature, which is the air which is leaving the radiator, and the water temperature is jumping a little bit, but it's let's say 33 degrees Celsius, and this is the ambient temperature, 24.8. So I note down these values, and I will do some calculations on the chart and on the numbers, and I will also adjust the K-type thermocouple a little bit to get a better reading of the temperature, get more closer to this value here. And after that I will increase the current and do another measurement so we can get closer to the hot side temperature, and we will see what is the actual cooling performance. So with the current values and measurements, I found the DT to be around 40 degrees Celsius. So the DT now is the temperature difference between the cold side and the hot side. Of course, we are not directly measuring the hot side because we are measuring the water here, and we are not directly measuring the cold side because we pass the heat through a Peltier unit and half of the heat sink, but still it is something. We do both errors, or we do the errors on both sides, so maybe it's a systematic error. But now it's this doesn't matter. What matters is that now the QC, the cooling power, is around 32 watts, and the wattage, so the I times U, is around 67 watts. So as you can see, the water system has to deal with, let's say, 100 watts of heat. And now you can see that the temperature is still stable, so it can do the work quite nicely. So what I do now, I go up to around 10 amperes and see what happens. So I turn on my voltmeter here. Maybe I turn on the light so you can see the numbers. Hopefully this is better. And then of course I turn on the ampere meter, reset, and then we are aiming for 10 amperes. Not so bad. So now this will change, of course. So what I do, I let the system run for 10 another minutes, and we will see how the numbers develop here. And after that we might do the next type of measurement. So I waited enough, and I think no more temperature change can be expected from this kind of setup or conditions. So let's measure everything now, and then I also try to measure the current as usual. Almost exactly 10 amperes, and the voltage is almost exactly 11 volts. So now we can see this is 110 watts of wattage or power output, without the QC of course. So at least 110 watts are appearing in the cooling system. And then the next thing that I should do is I will do some calculations. I will just check the numbers, and then I come back and increase the power. So I think I waited enough, and we can see the numbers. So the current is almost exactly 10 amperes, and then the voltage is almost exactly 11 volts, and then the cold side is almost minus 12 degrees Celsius and 33.6 degrees on the water temperature, and that's almost the same here, channel 3, which is in the tank there, and minus 8.2 with the K-type thermocouple. And I just could not really adjust the thermocouple, so it is not touching the heatsink in the same way, because that's just touching one point on the heatsink, while the chip, which is measuring the temperature here, is squeezed in between the two fins here. So then that is in a better thermal contact with the fins. So what I will do now, I will just do a few calculations, and then I will increase the current and see what happens. Or actually now I can increase the current to 12 volts, 12 amperes without any kind of calculations, and then I can do the calculations afterwards, because now I took a picture of this setup, so I have all the values. So what I do now, I go up to, let's say, 12 amperes. So now we are here, but of course this will change a little bit during the consolidation of the values here. But now we are at around 13 volts and 12 amperes. We will see what happens with the water. The water should go up now significantly, because we introduce a lot of heat into the system. But let's just wait and see what happens in a few minutes. So it seems like that at 12 amperes, or let me measure it precisely. Yes, at 12 amperes the temperature started to reverse. So now we are 1 degree above the previous temperature here and here as well, while the water temperature got higher. So that means that the cooling cannot efficiently remove the heat from the hot side. So that's bad. So what I do now, I go back to 10 amperes, and then I turn on the Peltier unit on the top. So let me decrease the current. 10.03, and you see that the temperature started to decrease again, and also on the water here. So now let's turn on the power supply, and now I turn on the top unit with 1 ampere only, and then I will go up step by step. So I set the limit of the power supply to 1 ampere, and now I turn it on now. And it seems like 1 ampere and 3.2 watts are coming through that device. I cannot measure the voltage, but I can measure the current. So let me do that. So 0.98, that's pretty much 1 for me. So now we added some heat load, of course, to the whole system, so maybe this will be worse than before. But what I do now, I will let this system run and we will see what happens. But first of all, I need to bring the charging cable for the camera again. So I waited enough. This is the current on the bottom part, and this is the voltage on the bottom part. And based on the readings of the top power supply, I have 1 ampere running through the circuit. I can actually measure that, and that's correct. And then 3.93 volts. So what I do now, you see that the water temperature hasn't really increased, but we are at minus 32.9 degrees. I increase the current to 1.5 amperes on the small units, so the top units power supply, and see what happens. So 1.5 amperes and 5.6 volts roughly. So what we should see now is the temperature should further decrease. So let's wait another few minutes. We see the time here, so I will come back and check what happened. So we waited enough. If you check the time, and you can see that the hot side temperature regarding water hasn't really increased according to this unit. Of course, if I check the number 3 sensor that is here in the tank, you cannot really see the tank, but it's in that direction. The pump is down there, and this is like the very bottom of the tank. So that temperature is 42 degrees. And then maybe I can believe that. I can try to measure with an infrared thermometer this. So let's see. But I don't. This is actually showing 32 degrees. Of course, this is not the best evaluation technique. But yeah, something like this. And if I just measure the fans, the back side of the radiator, I see 35 degrees if I round it up. So we are somewhere between 34 and 42 degrees Celsius regarding the water temperature. And as I said, I left the big power supply, which is running the bottom unit, at 10 amperes, and we are 1.5 amperes we are at 1.5 amperes with the top unit. So I move up, because you see that the temperature now is 38.6 degrees or 35.2. If I check this, this is not visible, so I will try to do something for you so you can see it. So maybe if I rotate it, yeah, should be this. This should be helpful. So now we have these things. So I go to 2 amperes and see what happens, because as compared to the previous power setting or current on the top unit, I could not really increase the temperature here. So that means that I did not really add too much extra power, which has to be dissipated through the or carried through the bottom unit. So let's increase the current to 2 amperes and see what happens. So now we are at 2 amperes and we see, but here you can already see that the temperature is going down, I guess. Yes. So let me check the current. Two amperes. So the power supply is nicely working, and now we are just waiting. So now it's 32 here on this watch. So we wait a few more minutes and see where the temperatures will be stopping. So I am back after roughly 5 minutes, and we could see that the temperature there is still okay, 34.4 degrees Celsius. So we are, let's say, 10 degrees above the ambient temperature, which is 25.4 degrees, and the thermometer is somewhere here, this guy here. So that's what we have, and the chip, which is stuck between the two fins of this heatsink, is at minus 41.9 degrees Celsius, and also this guy is starting to approach the minus 40 degrees. So minus 41.92 on the heat sink of the cold side, and that's pretty nice. And we did not increase the temperature. So now I go for 2.5 amperes on the hot side, on the cold side, so the top side of the stages, and see what happens. So let's increase it to 2.5 amperes, and now it's 9.5 volts. So let's say 25 watts of power plus the small cooling power here. So let me just measure this thing to be sure. So we got this 2.55, and the temperature dropped now to minus 42.42 degrees. So that's quite nice. So what I will do now, it's 39, so I wait another 5 minutes or so, and we check all the temperatures and see where we end up. Okay, so it seems like we are nicely able to maintain the temperature of the water, so it still hasn't surpassed 35 degrees Celsius, and the cold side temperature based on the chip, the LM335 thermometer chip, is at minus 43.62 degrees Celsius, and also based on the K-type thermocouple we are almost below minus 40 degrees. Now I just put this cap on the top because I was thinking maybe some heat is going in through this thin layer of plexiglass. And now I will probably extend the time of the experiment by several minutes, maybe 10-15 minutes, but I will use this and I will measure the top of the heat sink. So what I do now, I will try to be quick and try not to be clumsy to mess up everything. So I remove the lid here. There is a plexiglass on the top of this, if you cannot see it from that perspective. And I will just do a measurement. So now this is working. And this is actually showing much lower values. I mean much higher regarding the temperature. And I guess the reason for that is that partly I'm trying to take a measurement with the infrared thermometer on a metal surface, on a shiny metal surface. Maybe that's not the best idea to do so, but you can see that these two other devices basically show the same temperature, so that cannot be the problem. So what I do now, I increase the current by ½ ampere again on the top stage, and we see what happens. Of course, now the temperature went up a little bit because I introduced warm, fresh air in this chamber. So I just put this on to cover it, and maybe it will be cold again quicker. So I go to 3 amperes on the top, and at the bottom is still at 10 amperes, 11 volts. I can check this. Yes, a little bit dropped down, so now it's 10.85 volts. And let me check the current for you. (10.01). That's quite close to 10. So this is 35 degrees. So let's see what happens if we put more heat load on the bottom part by increasing the current running through the top part. 3 amperes. And now at 3 amperes the voltage is at 11.8. So let me measure the current. Or like this. 3.01. That's acceptable for 3. Then 52, so I wait, I don't know, until 10, and we see what happens with the temperatures. So as you can see it on the numbers, the temperature increased a little bit, and also here we have like 0.5 degrees Celsius increase. It's not so bad, but it's noticeable. But since there is an increase, after I increase the current from 2.5 to 3 amperes on the top side Peltier, which is on the heatsink, I decided to go back to 2.5 amperes and then increase the current on the bottom device, which is now running at 10 amperes. So first let's go back to 2.5 amperes, and I did that now, so I measure it just to show it to you. So this is the current on the top, and now let's check it on the bottom Peltier or bottom stage. So 9.96. So what I do now, I try to go 10.5. So this is our value now, 10.47. So 10.47 amperes and 11.47 volts. So now we wait and see how the temperature develops. But I already see that the temperature started to decrease again. So this is a good sign. So now it's at minus 42.92. And this also started to change. So now it's 10:05, just changed to 5. So let's wait 5-10 minutes and see how the temperatures are developing, and then we can decide whether we should go up with the current. So first of all, let me check the current again, because that is always changing during the test. So I check the current of the bottom unit. 10.5, it's very precise, 10.5 amperes and 11.5 volts. That's very good. And you can see that this guy went down and this guy went down minus 44 degrees, and this guy barely changed, 35.5 degrees Celsius. So what I do now, I should increase the current on the bottom device again to 11 amperes. So I will do that. I slightly change the power supply, and I go to 11 amperes, and I stay at 2.5 amperes with the top unit. 10.91. I increase just a little bit, and maybe I will slightly overshoot 11. Okay, let's stay with this, 11.16, and this is at 12.25 volts. So let me just put down this here, and let me take a picture. So this can be used in the video, so I can see all the numbers precisely, and I can show some calculations to you. So I turned off the voltmeter, turn off this, and we wait another 10 minutes. So now it's 13, so let's wait until 23. So seems like that we are stuck at this temperature right now. So we are at minus 44.02 degrees, and this is also almost minus 40 degrees Celsius. The water temperature slightly increased to 36.4 degrees Celsius, but that's not a big deal. But I believe that as I increase the current on the bottom unit, or in the bottom unit, I also increase the cooling performance a little bit. So now, instead of going to 3 amperes with the top unit, with the 3 ampere unit, I will go from 2.5 to 2.75 amperes and see how the temperature develops. So let me change the current. So 2.77 with the meter, and now we just have to wait and see what happens to the temperature. but it might be the case that it will be stuck at this. But still, the other unit is around 11 amperes and 12.51 volts. So that's what we get there. And then that's all basically. So now we have to wait another 5-10 minutes and see what happens here. But now you can see that this really doesn't move anywhere. So we might have to do something else. But this is already 4 degrees lower temperature as compared to the previous test with cheating. Because at that experiment I had cold water freshly introduced to the system, but here I don't have. But I had a different starting up strategy, so that might have made some significant change in the system, and I can believe that really works like that. So now let's wait and let's see what happens with the temperature. So as you can see, the temperature got stuck at this level, minus 43.72 and minus 39.4, and this is 36.7. So what I would see, or what I want to see, that what happens if I further increase the current on the bottom part. So now we are at 11 roughly, so I go up to 12 and see what happens. So let's accept this as 12 amperes. So 11.95 amperes and 13.26 watts. So we could see that the temperature immediately increased on the hot side, of course, because we increased the power. So we should see what happens now. So I just don't want to wait more, because I can see the trend of the temperature, which is now increasing, which is not good for us because we already reached minus 44 and we don't want to go above that. So what I try now, I leave the top unit at 2.75 amperes, but I move the bottom unit to 9.5 amperes. So let's see what happens when I do that. 9.55. So let's see, because now I assume that we are somewhere between the too much current, which provides too much heating for the bottom device, and between the too low amount of cooling, which of course will not cool the top device. So let's see what happens. But I can see that the temperature is increasing. So additionally, I drop down to 2 amperes with the top unit. So once again, 2 amperes on the top unit and roughly 8 volts. And on the bottom unit, we are at 9.5 amperes and 10.6 volts. So let's see what happens after a few minutes. So I haven't been waiting for a long time, but we can see that the temperature started to increase, but the temperature on the hot side significantly dropped, 2.5 degrees roughly. So what I do now, I start to increase the top unit to 2.5 amperes and see what happens. So 2.5 amps on the top unit, which is the 3 ampere unit, and I will tell you the current. So 2.48 it is, and the temperature started to decrease again, so that's a good sign. So let's see what we get there, and then now I will wait more for real, and then we see how the things are changing. But probably that the thing is that that we are somewhere at the limit of the bottom device. So if we start to increase the current to get some more cooling power, maybe we will get too much current running through the device of the bottom device, and then that will increase the temperature too much, and then of course the whole system just collapses and starts to warm again. But here we passed the minus 43, so this 2.5 amperes was a good idea. So we are at minus 44.12 degrees, or minus 44.02 degrees Celsius. But what is the most shocking is that this temperature stayed lower than it was previously. So seems like there was some kind of transient when I decreased the current from 12 amperes to 9. Now, as everything started to reach the equilibrium, the numbers look better. So what I do now, I go to 3 amperes with the top unit and see how the temperatures develop. Because this 34.4 degrees suggests that the heat transfer is sufficient, and then we can see if I further increase the current on the top side, can we remove that heat that we generate? That's one of the question. And is that heat or is that extra power is enough to further cool this down? So let me increase the current. 3 amps, according to the power supply at least. .02. So now the temperature went down to minus 44.22. Of course, that's just maybe some kind of oscillation of the values, whatever. So let's see in a few minutes what happens, and then we come back and do some kind of discussion. Okay, so this doesn't seem to work anymore. As you can see, the cold side is relatively cold according to the water's temperature, but even the other thermometer is showing 41 point something, 42 point something degrees Celsius. So that's fine, but I cannot really get the nice combination of the two voltage values and current values for the different power supplies for the two Peltier units. So I think the most important thing that we could change here is the temperature. So what I will do, I will attach a hose to this valve on the bottom of the picture, and I will remove the water again until a certain level in this water tank and replace it with some cold water. And now, of course, I don't have the water from the fridge, but it's only from the tap. But I can check the temperature of it and we can see what is happening. So now I have again half a liter of water, and you can see that this is like let's say 12 degrees, something like that. That's quite cold. So even lower, maybe 11, but it doesn't matter now. So I just put this here, and I try to make everything in the safest possible way, because there are high currents running here and it's electronics at the end of the day, so you don't want to mess them up with water. So let me just work a little bit. So everything is at its place. I have to open the valve down here. So I will slowly open, check the water level in the water tank, and then replace the missing water with the roughly 11 degrees cold water. So I just open the valve slowly so I can keep up with the pace. So now as I added some water, some bubbles also entered the system, which means that you can hear this sound because those bubbles got stuck in the pump. So if you check it now, this thing is decreasing, and you can see that we are below 30 degrees Celsius on the other thermometer, and we are below 44 now. So this is another I don't know, testament or sort of proof that the cooling is very, very important, of the cooling of the hot side, and also the monitoring of the temperature, because we could see that we are so off with the values, so that's not so good. So now I close the valve, and then I just put this very, very small amount of water in it. Perfect. So this will probably reach -45 degrees in very short amount of time now. There we go, I saw it. So -45 if your cold side is cool enough. So I can take this time while the water is cold enough, and I crank up the current on the top unit to, let's say, 3.2 amperes, and see what happens. As long as we get this, I don't know, high enough to flip the effect, then I guess we can drop this value further. So now 3.2 amperes are flowing through the top device. Which is about right, and 12.71 watts. But now you see that it is maybe reversing. So we reached some sort of, let's say, critical value for this particular system. So then the hot side of the bottom is getting hot again, and then we don't get the sufficient cooling, therefore we cannot really do anything with the excess temperature coming from the top, from the cold side. So this is what we have. So we could see that the way we should sort of start up this system is that we should first determine our DT by just cooling down the bottom device and checking the temperature on the top of the heatsink. So of course this will be a slow process, but at the end, due to the heat conduction between the two units, we will be able to see the temperature reached on the cold side of the bottom unit. And once we have that, we can sort of obtain the values regarding the current and the voltage and the QC. And based on that, we can start our top device, which is the TEC12703 in this case, which is down there. And then we can see whether the bottom device can keep up with that kind of current or not, or that kind of heat, to be more precise. So that's what we have there. And then we could also see that the hot side temperature, so basically the temperature that the water reaches here, is very, very, very critical, because you could see that now we are 1 degree above that value that we were able to reach when this temperature was roughly 4 degrees colder. And then it would be very, very nice to be able to measure the hot side of the two Peltiers. I have some extra, so I might do a notch and somehow put a thermocouple in that notch, but I have to figure out first how to cut or grind the surface of these aluminum oxide ceramics to not destroy anything. And also I have to see if I can get some smaller or thinner thermometers. I believe that there are some sort of platinum thermometers which can be very, very small, but they are also very sensitive, so maybe I would destroy them when I sandwich these things together. But maybe if the groove or the notch is deep enough, I don't really put any stress on it. So maybe I can work with that as well. So now I just finished the experiments because it's a bit late. And what I will do now is I just shut down all the equipment. Of course, what you should do is first you should shut down the top one, because that's I mean, if you shut down the bottom Peltier, the top one is still running, but there is no heat transfer other than the heat conduction of the material, and that might destroy your top device, because the top device would become very hot. So first, turn down the voltage of the top device, and then remove the sockets or the connections of the power supply, and after that you just turn down the voltage of the bottom device and still let the pump run for 1-2 minutes just to equalize the temperatures. And after that you just shut down the pump and the rest of the things. And actually I will do a time lapse of this just quickly. So I will just record the time lapse, record the shutdown process as a time lapse video, so we will see how good is the insulation, so we can see the temperatures. But of course I have to shut down the pump for that as well, quite quickly, because otherwise I would constantly transfer the warm water to the bottom of the bottom device, and that would mess up the heat transfer here. So to decrease that effect, I just stop the pump as well. So I hope that this video was useful and instructive and informative for you. If you liked it, please leave some comment if you want something to discuss about this experimental setup. And also please subscribe, and see you in the next video.